All right, excuse me. Let's get started. So we have our final on Thursday, and then only 2 people talked to me about taking it early, so it is in the testing center. And then if anybody else wanted to take it early or at the testing center, just let me know so I can make another copy and let them know ASAP. And then presentations went really well. I'm just tallying up everything. I was hoping to have those back, but I'm only slightly behind. I've been trying to get everything else caught up in your grade book. I think I forgot to hit post. So I'll try to get back. Sorry, let me post all your grades that I've been working on. I have a fat stack of papers, so if you're around, take your papers. I have them. And then just double check your grade. Blackboard has been even more finicky than usual, I swear, this quarter. So just make sure that everything is saving and good. I'm not sure if you can see all your grades because of how Blackboard is, but just double check with me if you have any questions, and then just get everything in. Any questions before we get started? So it's kind of a free-form review today. I figured we would go over our quiz though, like we promised, and then we can do kind of similar questions and anything else we need to look at. All right, so let's look at number 1 here from our last week's quiz. And if you weren't here last week, make sure you get credit for it. So which of the following can be an isomer of a carboxylic acid? So what's the answer to that one? Kind of what's a carboxylic acid? How else could you, excuse me, rearrange this kind of formula, right? What is the same groups? So what do we think? Ester, good. And so the ester, right, has the double bond, it has an oxygen. So it's similar to the carboxylic acid, right, except we just kind of move these carbon groups around. And then, so which one is an isomer of a ketone? So good, aldehyde, right? So the ketone is a C, double bond O in the middle. And then the aldehyde has that on the outside there. And then, okay, which of the following is an oxidation product of a secondary alcohol? So which one was this? So kind of what's the secondary alcohol? Kind of what's the problem, right? We were saying that it only undergoes one oxidation. But kind of why is that? And it's kind of hinted in the product, right? Like which one does not have the hydrogen? Ketone, good. So, right, we make the ketone, but then like we're saying, the oxidation stops there at the ketone since it does not have that hydrogen to lose. And so then this is kind of almost a follow-up to 3 in that what's the oxidation product of our aldehyde then? So where it does have the ability, right, to lose a hydrogen. So then what's the oxidation product of this? Nice. Carboxylic acid. And again, right, there's the distinction. So no H to lose. So it cannot, right, make the carboxylic acid. Which of the following pairs of molecules are isomers of each other? Good. So butanol is the aldehyde, right? Let me try this again. So 1, 2, 3, 4. 1, 2, 3, 4. And then butanone. One, two, 3, 4 there. And then these other ones, right, have just different groups. So methylbutane and methylbutanoate, right? So this has too many oxygens. Same thing, you have the OH versus these two O's of our butanoic acid. And then, right, butanol, we have our OH versus butanone there. All right, what is our IUPAC name for this one? So you said, so let's look at, we have 1, 2, 3. So we have 4 over here, right? And then our O8 kind of group is 2 on one side. And it might be helpful, let's see if I have these notes. I happen to click on them, right? So kind of look at our 2 different sides. So we have our group and then ethanoate here. So going back to our review, sorry. So then, what do we get for this side? So 1, 2, 3, 4. So butyl ethanoate. So going back, so it's made from 1, 2, 3, 4. So it'd be made right from this carboxylic acid and then our alcohol 1, 2. So ethanol there. I'm just flipping back to our notes here. Right, so we can compare that. I was making sure I got the group correct. I think I flipped it. Yeah, I was wondering if I did that. Okay, so then, sorry, this is not the name. So then, what's our name over here? Sorry? Yeah. That's so ethyl butanoate, sorry. So 1, 2, 3, 4. Oh. Butanoate. 1, 2, 3, 4. So yeah, sorry about that. So ethyl butanoate. Does that make sense to everybody now? And so yeah, coming from these two pieces, the carboxylic acid and the alcohol, right? So this O is actually from the alcohol. And so remember, right, this leaves, so it's a condensation reaction. All right, and then our last question was draw our structure. So cis 2-bromo-cyclohexane carboxylic acid. And so I'll just draw my cyclohexane carboxylic acid. And then it should be cis though, so then trying to draw it on the same side. 2, so then it should look something like that. And then you could draw them both dashed and down as well, so that would be the same answer. And then, sorry, just scrolling back up from 1 through 4 in case people missed it. Any questions about this one here? The quiz or anything else? So let's go back. Sorry, I'm trying to pull up those notes. So we have, right, our primary alcohol is attached to an alcohol and then 2 other hydrogens. And so that's what makes it distinct, right? So that's why it can undergo 2 oxidation steps, right? So it has 2 hydrogens on it for 2 oxidation steps. And then going back to these notes from chapters P and R, right? So we looked, okay, strong oxidation. We made the aldehyde just like we saw in the quiz. And then the fact that we can lose a hydrogen again, right, means that we can take this, and now this is on the next page in our notes, right, where we said, okay, then we take that aldehyde from the primary alcohol, we can do it again and make the carboxylic acid, right? So just like methanol here with potassium permanganate. And then, right, so compare that, just look at your secondary alcohol. And so now only 1 hydrogen that it's attached to. And so that's why, right, it loses that one in the oxidation, and then we're left with the ketone. So no hydrogen, so now we can't go on. And so that's what we have down here, right, that we can't undergo, oh, sorry, that's for the tertiary, but the secondary, right, cannot go another oxidation step. I think that's on the second page of those notes, right? Where is it? Well, we could draw it. And then the tertiary alcohol, if you were asking, right, has no hydrogens attached to it. So this is the tertiary that was drawn down here. So the tertiary alcohol cannot undergo oxidation. All right, let's see. So you'll have like a little bit of half-life stuff. Let's try one. So let's do, so what fraction of material will remain, and let's do after 4 half-lives. So what do we get for this one? You can give me a percentage or a fraction. So 1/16, excellent. And so you could do, right, the formula 1/2 to the n for the number of half-lives, especially since we're kind of using some other, I'll call it brute force, cheat sheet and methods. So I would again kind of brute force it, right? You have 100% at 0, 50 or half after 1, 1/4 or 25% after 2, 1/8 or 12.25 after 3, and then right on and on. And we also had our formulas as well that we looked at kind of second quarter, but kind of encouraging, right, other ways of solving it. You could have stuff about your activity series, like giving some metals. So what is most active? And then just, yeah, multiple choice things about DNA, coordination compounds, a little bit about formulas. Let's try, we haven't done a plating out one. Let's practice this. So let's do how much current is required to plate out, and let's do 0.05 grams of copper from a copper sulfate solution in 10 minutes. So go back through your notes. What formula was this? So I'll give you some time. Yeah, let me. So yeah, so Faraday's constant. I have it as 96,485 coulombs per moles of electrons. All right, before we go over this problem, the one about plating out our copper, I wanted to address a question in the chat. And so the question was asking about drawing out aspartic acid. So I think it came up in one of your homework. And so the question was, do you put the hydrogen, oh, sorry, let's resume it. The hydrogen, right? So on your compound chem worksheet or chart, so I did print out compound chem cheat sheets. So if you need one, grab one. But right, just looking at how they drew it on here, they just so happen to draw the deprotonated form. So I would have to look back, like they may have selected this. Maybe that's how it exists at pH 7. I'm not really sure why they did that. It's some sort of pH dependence. But for our purposes, it really doesn't matter. So I think the chat was saying that on your answer key. And so if you look at some of the biochem homework answers, and I believe this is the one in question where they're drawing out this group and they have the OH drawn there, right? I mean, like I said, it doesn't matter. So if you left it off and left it as a negative charge, it's the same thing, right? You're just talking about the protonated and deprotonated species. And again, just pay attention to the backbone. That's kind of what I was trying to get y'all to see, that you have your amine, right? Your carbon, your R group for our first amino acid, and then, right, amide bond, new carbon, and then that group, right, for the aspartic acid there. And so, no, it doesn't matter if you draw it with the proton or deprotonated. And then just do keep it right as a carboxylic acid, though, here, so we can see. Does that clarify that? And kind of make sense for everybody. And so that, again, applies to any of these amino acids. I think we looked at them kind of last week. I'll try to point them out again, the ones that are pH dependent. No, I'm doing a poor job at finding them. Oh, here's the other one, right? Lysine is another one. So they're showing it in its protonated form on this chart, right? This nitrogen has an extra hydrogen there. So again, it doesn't matter too much if you show it protonated, deprotonated, or in that case, neutral. And arginine might be the other one that you see, right, in different forms, but it doesn't matter too much for our purposes. We're not getting into the specific pH and what it's doing. All right, so let's go back to this one then. So kind of walk me through what do we need to solve for this problem. So I mean, we had Faraday's constant, so that was a pretty good start. So then how do we get to moles of electrons then? We have 0.05 grams of copper. Yeah, it didn't specify. Well, so we have time in 10 minutes, so we can convert that to seconds. Is probably what we'll have to do. So what, that's 600 seconds. But I still need, what's the big thing I'm missing? Yeah, there we go. Mass, right? So we need to find moles of this. And then if you didn't already do this, right, figure out how many electrons are involved in this process as well. So we're looking at a 2-electron process. All right, so let's do that. So let's find moles of copper. So 0.05 divided by 63.55. And just make sure you check my math on all this. So then you get that many moles, but then we said it was okay, a 2-electron process. So now 0.00157 moles of electrons. And so then we want to convert, right, our moles to charge from our Faraday's constant. So we can figure out, right, our Q by our Faraday's constant times our moles of electrons. So that gives us, right, how many coulombs we need. Sorry. So about 152 coulombs rounded. So I'll leave it 151.8. And then, like you were saying, okay, well, we have to figure out the time, right? So we converted our 10 minutes to 600 seconds, right, to account for our current. And so now to find our current, we can take our Q over T, so 151.8 divided by 600 seconds there to figure out our current. And so we should get a current of 0.253 amps there, or coulombs per second. questions about this one? So let's try another type of problem. And so now we'll kind of switch gears. And so this is not the same molecule you'll be shown. You'll be shown something else on your exam. But the idea is for the identified parts, identify our hybridization. So let me circle some. And let's do this nitrogen here, this carbon, and this carbon, and that one. So 1, 2, 3, 4, 5 highlighted carbons there. And the nitrogen, sorry. So take a few minutes to look at that. So what's the hybridization? And remember, hybridization is SP, SP2, SP3. So just take a few minutes before we go over it. All right, let's see what we got. So let's start with this one up top, the carbon and our carboxylic acid here. So what's its hybridization? SP2, good. What about this one here? SP3, good, right? So that one did not have a hydrogen drawn on there, so it's a little deceptive. What about this nitrogen? So that's a good guess. I'd probably go SP3 though, just because of the lone pair. And then the only reason though that I wouldn't go SP2 on this is because there's no like arrow pushing hybridization, because that is always a hard call of like SP2 versus SP3, because it goes back to sometimes nitrogen can be SP2, right? So you have nitrogen SP2, and then it's a question of whether those lone pairs are then going to do pi bonding if it is an SP2, or I think this one is SP3 because there's nowhere for those electrons to double bond. So I'm assuming they're just hanging out in SP3 configuration. What about this one? So SP3, and then this carbon on our aromatic. SP2, good. All right, and then we also had, so kind of shifting gears again. So we did our nuclear reactions. So we'll have some balancing equation ones. So let's see. I was trying to find a good product here. So let's see if we can balance this one. So we have 59 cobalt. And what particle is it bombarded with to give us 60 nickel and a neutron? And I'll sketch out another one while you work on that. So what did we get for this top one, right? So you have to kind of add it up on your product side. And then, so what was the mass missing up top on the mass number on the left side, on the reactant side? Two, right? So good, right? So you have 61 minus 59. So, okay, so we have 2. And then what's missing on bottom? 1. And so this matches with hydrogen. So, right, kind of a hint at another process, right? So you can initiate a nuclear reaction by bombarding with deuterium. And so this is the result of that. Questions on this one? I'm not sure because I mean, I think it's just like called deuterium. I know they also use like tritium too, right? For I'm not sure actually what they do with it. I mean, wasn't that like the latest thing that they're hyping as like if we go to the moon, we're gonna mine like tritium or something, and then I don't know what we're gonna do with it. I don't know. People have crazy ambitious plans, but all right. And then, so what was missing in our product for this side? So manganese, so that'd be 25. And then what's the mass still? So 55, 25 manganese. Good. All right. Questions? I'm debating. I don't know if we should take a break or just kind of keep going. How are you guys feeling? I could also leave you with a question. Maybe we want to just keep going. So let's try a different type of question. Like I said, we could take like a short mini break too while people like stew on this question. But let's kind of look at this compound. So cobalt hexa-aqua compound, right? 3 plus. And so what's its D count? And then is it high spin or low spin? What do you kind of predict? And then like what other evidence, right? What's kind of the difference between these two? And so I'll give people at least like 5 minutes to kind of come up with an answer and sketch something out. So like I said, if you want to use a bathroom or anything, this might be a good time. We might just keep our review moving, and then we can always end early and ask questions and all those sorts of good things. All right, so it looks like we have some ideas in the chat. And so let's kind of go over what everyone is thinking. So what's our D count on this compound? Right, we have cobalt 3 plus here. Water's neutral. So how many electrons does cobalt have? So 6. So D6 there. And then, so we don't necessarily need to be right. We just, again, kind of have to compare our predictions. And so what do we think? High spin, low spin, kind of what's the difference? And so let's kind of start. What if we have a high spin complex? Right, what does that mean then? And so high spin, so octahedral, so I'm drawing out, right, the octahedral splitting pattern. So you'd want to draw, right, this on the exam. Then let me double check the exam. I'm pretty sure it's an octahedral complex. Yeah. So we're just going to ask about an octahedral complex. And so then if it's high spin, then we expect it, right, to have a weak gap here. And then it would fill. So 1, 2, 3, 4, 5, 6. And so what would be, well, let's compare. So now let's look at our low spin possibility. So 1, 2, 3, 4, 5, 6. So now all paired. And so what's the difference between these two? What are we going to be looking for? Yeah, so either whether in this case, right, it's going to be paired, so this is diamagnetic. And so we would probably expect this to be, right, if it was larger, so caused from a large splitting. And then, so a good comment too that was brought up in the chat is that water is kind of like in the middle, roughly, of that spectrochemical series. Let me pull up. I try to pull up some notes on the side on that. Oh, now I lost them. So I don't have our class notes. Oh my gosh, sorry. Handy, but looking back, so this is a typical chart that we saw, so kind of refreshing back. And so water is kind of in the middle, so that is difficult to predict, right, whether it's going to be weak field. And so like we said, these weak field ligands, right, cause a smaller gap, and then we would expect them to be high spin, right, because they can make that energy gap. Versus our strong field ligands, so CO, like we had mentioned, was particularly strong because it did that pi back bonding, so then it made it have a larger gap, but then it's going to be low spin. And so that's right, kind of the debate. But like y'all were saying, okay, this is what we predict, and so this is basically what you'll do on the exam, right? You write your D count. This is what I expect if we have a high spin complex. This is if we have a low spin complex. And then looking for the comparison. So our high spin complex then would be paramagnetic. And then, right, we need more experimental evidence at that point. So need some sort of evidence. We also didn't give any sense of color with this or anything. So that's not going to be on the exam, but just kind of thinking back to like what you would do in the research world. Well, you're going to be measuring this gap that's going to be dependent on the color. And then again, that tells you more information. All right, I feel like we're hitting this pretty good. Let's look at some kind of naming stuff. So let me see if I can draw some of these out. Okay, so this would be like a true or false, and the correct name is 4-methylhexane for this one. So look at that for a second. Why or why not is that true? And then while you're staring at that compound, I'll try to draw out another one. So what's wrong with the first one, or is it correct here? So false. And so what should we fix with it? Nice. So at the very least, it should be probably 3-methyl hexane. And then what do we think about this bottom one? I feel like I didn't do maybe the best job. Good. And so you didn't fall for the trick of I was trying to trick y'all into thinking butane, but 1, 2, 3, 4, 5, 6 is the longest chain. So excellent. So you said 2-methyl hexane there. All right, that's pretty good. Uh, then other types of questions. So like I said, you're gonna have to like identify polymers or potential copolymers on the exam. Ester, so naming the ester and then the alcohol and carboxylic acid like you did. Bit of metal naming, which maybe we should try to do some practice. And then writing out the peptide like we had mentioned. So that was on your homework, but we can always do another one. But I think as long as you have the backbone, you'd be fine. All right, let's try a few naming ones. So let's name, oh, that one didn't format very nicely. Okay, I'll just type it. So see if you can name this compound here. And let's try this one. Oh, sorry, CuCl4. And all right, try those 3 for now. So let's see how we're doing. What do we get for the first one here? So potassium, hexacyanoferrate 3. Excellent. And remember, it takes us 8 endings. It's an anion, so we name our cation. Hexa for the cyano group there. So good. And then right potassium, so we know this is 3 plus. So that's how you got. And then we have right 6 minus on our cyanide here. And then right to make it neutral, 3 plus. Any questions on that one? What about this next one here? So what's the oxidation state of copper? Right, balance it out. You got the ammonia here. So +2, good. And then, so what's our name then? So ammonium, and then tetrachlorocuprate, and then 2, good. Then our last one, so now this is, right, our cation again. Balance out our charge here. So let's see. So what's our oxidation state of copper here? Oh, sorry, cobalt, thanks. So +3, good, right? Balancing out those 2 chlorines. And anybody want to give the name or? That sounds good. So pentaamine, and then you said chloro, right? Chlorocobalt 3 chloride. Excellent. That was a mouthful there. All right, what other things do we have questions over? I feel like we hit all the main like exam topics. Like I said, kind of the rest of it is just identifying the polymers, and you're always just thinking about those amide bonds, right? Usually an amine and a carboxylic acid coming together to form that amide bond as well, or the alcohol, right, with the esters. Oh, and then, yeah, cis-trans naming. I didn't go too crazy on the organometallic compounds. There won't be too much. There will be some. I was trying to pull up, going back to the one that we did. Oh, sorry. Now I'm just flipping wildly. Where did we do it? Didn't we name an organic compound today? I was trying to find where it went. That cis compound that we named. Now I just feel like a crazy person. Oh, this is what I was looking for. Sorry. Like, there could be something like this, like the cis, yeah. Uh, so there might not be too much naming, but yeah, so there could be like something like this, right? So versus trans. So again, cis versus trans isomers. I'm not sure that I covered it though as heavily as I could have on the exam. That being said. Oh, the other thing we didn't go over, but we still might do, is the galvanic cell drawing. So remember kind of drawing that out with the beakers and the salt bridge and labeling those parts. So you'll probably have to draw one of those and again kind of labeling everything. Anode, cathode. I try to keep it, I think, somewhat light, hopefully, on the exam. Are there other questions or things that we want to go over? Review questions? So, probably gonna at least stop there for now. I'm gonna keep the stream going. I want to try to get back people's papers though, so that you can check your grades. But like I said, I'll keep the stream running. If something comes up in class, we can go over it. Otherwise, just get everything turned in any way, shape, or form. And then this is also like last call for posters or lab makeups or anything that needs to happen. So just let me know now.